section 2.6 is to understand shifting of functions. And basically that I can give you graphs of any shape, doesn't really matter what, and then you can be able to predict how a function is going to look when it's been shifted. For instance, let's see, I got an extra function turned on here someplace. Let me just redo this. There we go. So here's our graph, j of x. What do you think is going to happen when I look at j of x plus 5? How is that going to be shifted compared to the original graph?
Left by.
So left by 5. Great. So once you understand these forms, we can make predictions for lots of different graphs. So let's kind of keep track of these for ourselves. Let's see where it go. Here we are. So shift to left by 5. The next one has us at j of x plus 4.
That's what I said, shift to left by 5.
And that one's going to do what?
No, we're
Up by 4. Good. Let's just do that one.
I was looking up.
Up by 4. Looking good there. Shut this one off. Let's move down a little bit further. Now here I kind of regret my choice of j of x because it has symmetry in a couple ways. It's symmetric across the x-axis and symmetric across the y-axis. So the correct answer here is that it's reflected around the x-axis. So that would be the answer that I'd be looking for. But just so that you have like a little better perspective on that, let's take a look at a little bit wilder function. Yeah, it's here, this one. You got a question?
Can you say reflected across the x-axis, or does it have to be around?
I guess I would take either one, across or around. But yeah, those say the same thing to me. So in this case, this is a kind of a hodgepodge of a function. But let's take a look at y equals negative f of x. And now it's a little bit more clear that this has been reflected around the x-axis. Whereas if I have that negative not on the outside, on the inside, this reflected around the x-axis, what do you think this is going to do? Reflected around the y-axis.
Oh.
So it's just a mirror image around the y-axis. So, okay. So the correct answer for that next one down there, like I said, is it was reflected around the y-axis. Moving down to 1/3 of j of x, let's take a look at that one. So let me go back and here. So 1/3 of j of x, this is going to shrink the graph in the y direction. So it's 1/3 as tall as it was. The points where it was 0, it's still 0, but the maximums here, this one here is at 0.205. This one should be at 0.615. 0.616, all right. There's a little rounding error going on there, but it's 3 times as tall. This is 1/3 as tall. So it's shrinking things in the y direction. You can see that same effect down here. If you turn on this graph and start playing around with the slider, for values of a that are greater than 1, it's going to shrink, it's going to stretch the graph away from the x-axis. Then once you get between 0 and 1, it's going to shrink the graph in the x direction. So, depending on the size of that coefficient, it's going to do one of two things. It's going to stretch it or shrink it. And I think I've got that listed for us here. So between 0 and 1, it's going to shrink towards the x-axis. A is greater than 1, it stretches away from the x-axis. And now we can start putting these things together. If you have a couple of these things in combination, for instance, j of x plus 3 plus 2, now you've got 2 shifts going on. What are those 2 shifts?
Left 3, up 2.
Good. Left by 3, up by 2. J of negative x, again, that reflects around the y-axis. So be careful on that one, even though the particular example I gave you guys, it didn't look like that. Let's keep going on the back side of things. More 1/3 of a function. This time you got a new function, so let's shut off these two functions. Let me go all the way up to the top. There we go. Turn on a new mystery function. It's that one. I like this one because it's not symmetric with respect to the origin like our first one. So that when you do 1/3 of something, you can see, okay, yeah, this is shrunk in the y direction. Or this one, it's a little bit more clear than it was with our previous function. What's going to happen if I have a negative out in front and then an x plus 4 here?
Reflect across the x-axis and then left
Across
4.
Good. The negative reflects across the x-axis. The plus 4 is going to shift to the left by 4. And that's not affected. The shift isn't affected by reflecting across the x-axis. So, bam, there you go. This one's a combination. G of x minus 4 plus 3. What's going on with that one? Right 4 and up 3. Got to move the graph a little bit to see that. So looking good there. Let's just kind of catch up with things over here on our handout. G of negative x. How's that one going to change things?
Reflecting in across the x-axis.
Around the x-axis? All right, y-axis, yeah. I thought I heard an x-axis. Good. It's going to be flipped around the y-axis.
What's the difference?
Well, let's take a look. Yeah, I mean,
You have to see where it flips. Like
yeah, so
outside is
if it's on the inside or the outside is what makes the difference there. So let me go back to this one. I mean, here the negative's on the outside, right? So it's going to be flipped around the y-axis or the x-axis. So the point which is here at -8 and 1 should be down here because you're going to change the y coordinate. It's going to be negative of what it was. So I should have a point down here at -8 and -1. Let's see that that's true. And bam, there it is. So in changing things this way by putting a negative out front, you're really multiplying the y coordinate by a negative. So what was happening above the x-axis is now happening below it. And what was happening below it, -3, -4, should now be happening above it at -3, +4. So it's just switching the signs, and that switches sides of the axis. Same thing's going on, except with your x-coordinates here. So I had an x-coordinate, for instance, at -8 and 1. Well, I get that same point over here at +8 and 1. So you're reflecting things in the x direction. So these are mirror images of each other around the y-axis. Let's see. Now the last thing to look at, well, almost the last thing, is what happens when we change the value of C. I gave you 3 different kind of tests here to run through. Let's get back to this and shut off. Let's see, which ones do I want to shut off? I want to shut off this graph. Move on down to the last mystery function, which, okay, looks kind of like the first one. But this time, let me turn on another graph, and I can start playing with this. And it kind of looks like a slinky or something like that. It's an accordion squishing it. So the terminology that I'd like to use is something like the fact that it's squished or shrunk along the x-axis. That's the direction in which it's changed, is along the x-axis.
I like the
Now it's getting, yeah, I know. Somehow I don't think I could write a textbook with these terms in it, but I'm not trying to write a textbook. I'm trying to convey to you what's going on here, so I feel I can be a little more informal. How about in the case where C is between 0 and 1? So let's dial that down a little bit. What happens when I'm between 0 and 1? What happens to the graph compared to the original graph? How would you term it?
That's the part I didn't get.
Just even in reflection or something.
To me, you're, what do you do in the morning? You stretch, yes. Yeah, so it's being stretched. Stretched in which direction?
X.
Yeah, stretched along the x-axis. And then the last thing that you could notice is that when C is less than 0, so let me just change this, let me just put in like -3 here. When C is less than 0, then the graph kind of gets reflected around the y-axis again. So same things are going to happen, it's just that now you reflected the graph around the y-axis. So C is less than 0 reflects things around the y-axis. There's a different behavior when you have that C on the inside as opposed to C on the outside. Now when C is greater than 1, it kind of compresses things. And when it's between 0 and 1, it stretches things. The opposite is kind of true with our last function here. Let me turn this graph off.
Quick question.
Yes.
You said when C is less than 0, what does it do again?
If C is less than 0, once it turns negative, it reflects it around the y-axis again.
Okay.
So that's just kind of going back to, these examples. This one has been reflected around the y-axis compared to the original one. So when it's negative, it reflects there. And then the same kind of things happen. That is, if C is between -1 and 0, it's going to stretch the graph, although it's already been reflected around the y-axis. And if C is less than -1, then it's going to shrink the graph. So the same two things are happening, it's just that they're now happening with the graph reflected. All right, so good question, thank you. Let's get rid of this one. And there we go. So coming down to here for our last mystery function, fourth one, a couple things can happen. Let's see, we'll play with them this way. So we'll start out with D equals 1. Here's your graph, looks like a couple sawteeth. Yeah, looks like a sawtooth function. If we increase this, then what's happening to the graph?
It goes up.
It goes up. It's stretching in the y direction is what's happening with that one. And when this D is between 0 and 1, then what happens to the graph?
Shrinks.
Yeah, it shrinks your graph, right? So a couple of those two things are happening. And what do you suppose is going to happen if I cross over that line 0? What do you think is going to happen to the graph?
Reflect across that.
Yep. Now you're going to reflect across the x-axis, and you're going to get the same kind of shrinking and stretching that you did before. It's just that now it's happening below the x-axis. So, cool. Well done on that one. So, what's the importance of understanding this and being able to do these kinds of things? Well, let me give you an example from my trig class. And let's see, that example is right here. This is data that I took from the average monthly temperature in a really cool city, Anchorage, Alaska. So each one of these points is the average monthly temperature in a particular month. Let me extend this data one more time by repeating it for another year. That's your other year. And when you get to your trig class, you're going to learn about something called a sine function, which this graph doesn't look like it's a really good match for this data, does it? So wait, how about if I shift it up a little bit? So I'll find the average height there and I'll shift the graph up. It's still not looking that good. What if I stretch it vertically? Well, I can stretch it vertically by multiplying what's out in front there. So now, okay, that's looking a little bit better. And now I've got to stretch it horizontally. So I can stretch it horizontally by doing this. And that's looking a lot better, except now I've got to move it horizontally. So let's move it horizontally this way. I'll shut off this one. And ready, set, ooh, ah, bam, slides right into place. Pretty cool that you can move these functions around and make it match whatever kind of phenomenon you want. So let's practice a little bit, going back to, say, our intermediate algebra course, but taking a look at some of these functions anew. Let's take a look at 54 here. I mean, here you actually have the equation. I don't necessarily need to give you the equation. How would this graph be shifted compared to, say, g of x equals x squared?
Right, 4 up 3.
Right, 4 and up 3. Perfect. Let's move down to this one. Compare this to the absolute value. Say f of x equals the absolute value of x. How would this one be shifted compared to that graph? Yeah, left 4 and up 3. And now one thing we're going to work with more in this class than we did with our other class, Math 1150, is cubic functions. But it's the same idea here that we have with all our other examples. Right 3 and down 2.
So
Perfect.
you ignore the cube?
Well, you're starting out with the graph of a cube, and then it's being shifted to the right 3 and down 2. So let me put that one up here just for grins. We'll do f of x equals x cubed, and then g of x equals, what was it, x minus 3 cubed. How about x minus 3 cubed. Let me just take a look. Minus 2? Yeah, okay. Minus 2. And you can kind of see by comparing points, this point here has been shifted to this point here. So to the right by 3 and down by 2. So it's the same graph, it's just been shifted a little bit, that's all. And the nice thing is understanding these shifts allows us to really play with functions. It's also good from a point of view of you. As a student, you want to know and be able to look at a graph that you put in your graphing calculator and go, well, wait a minute, that doesn't look right because I expected to do yada, yada, yada. And if it doesn't match those expectations, maybe you go back and take a look at how you entered the function, because how you enter the function can make a difference. It's easy to make a typo with all this technology. All right. Any last comments or thoughts on shifting and stretching of graphs? All right, let's put this one to rest.